Yeah, so thanks for inviting me. So it's my pleasure and honor, to speak. So it's something on our effort on steering images by using MEMS devices.
Sounds great. Yeah, I look forward to your
Yeah.
presentations.
Hi, everyone. As I'm Yuzuru from University of Arizona. So I'd like to introduce our research effort in particular on a multiplexed image transfer and dynamic image steering for AR and other applications, of course, specifically with a MEMS, micro electromechanical system-based spatial light modulator, Texas Instruments Digital Micromirror Device. So, Carl, so the previous speaker did a great, job in terms of overviewing, what's the pros and cons of spatial light modulators, micro displays. So the topic of my talk is now steering. So either, for LBS type of projector or not just a point-by-point image generation, but steer entire image, so without using additional devices. So this is the front page of laser focus world. So this issue specifically talk about LBS, but so my talk today is not on this, not LBS, but something else. So before getting into in detail about what we are doing, so here is what I'm thinking. What's the benefit of image sharing? So then deliver photons to where photons are needed. So this is in time and on demand a delivery of images photons. So then what's the benefit? First benefit is now, so by steering image, so we can decouple FOV pixel count trade-offs. For example, so if we want to generate, display, large and high definition images, so we have to have, many pixels. Then how can we decouple, so this FOV pixel count trade-offs? And also, by steering image, so we can segment FOV. So for example, now just display what we need to display to part of field of view, while all the other FOV is blacked out. So in terms of a power consumption, this is a good approach. And also pupil steering, based on eye tracking and gaze tracking. So this can be also done by steering image. Okay, so then display resolution. So this is not a micro display, but now we have a standard definition, Full HD and 4K, 5K, 6K, and 8K, right? So then, so these are state of the art. But what if resolution could scale, say, 1,000 times? For example, now our eye, human perception eye, has approximately 75 megapixels. So that suddenly beyond 8K UHD and pixel counts. So then, if we want to scan entire body of ourselves by MRI, so that requires 520 megapixels. And if we want to image the neurons of human brain, so that requires 86 gigapixels. And finally, so this is a rather hypothetical, but if we want to use a spatial light modulator, so to do the photolithography for semiconductor chips, having 20 nanometer futures and 25 millimeter die size, so we need 1.6 terapixels. So then, apparently, so there's a huge, discrepancy. So between, what we want to display, even for an AR display device, and what we have so far as a display device. So then, what's the challenge? Well, the size and power consumption. So then, suppose you want to display, 75 megapixels, which is equivalent to our eye perceives. So then with state-of-the-art of pixel pitch, say a couple of microns, the width of display is about 18 millimeter. So then, suppose we have 18 millimeter in display, so right next to my eye. So this doesn't allow us this kind of nice, all-day wearable display. So then we have to actually decrease a pixel size or pixel counts, and without losing a number of pixels displayed, and as well as a resolution to be displayed. So then how can we do this? Well, then wavelengths or FOV multiplexing technique comes into play. So then let me overview our concept. So now, so our concept